All right, so welcome back, everyone. I'm very pleased to introduce Ilya Razenshteyn, who is a senior researcher in the machine learning and optimization group at Microsoft Research in Redmond. I first met Ilya when he was still a PhD student at MIT, and already back then it was quite clear to me that he was heading for a brilliant career. If you go to Ilya's Twitter page, you'll realize that he's not just interested in computer science, he's also very interested in health and wellness issues, and in particular how food culture affects health and wellness. So maybe it's actually fitting that SISAP 2020 is the first edition of the conference that has no unhealthy food whatsoever. Well, okay, joke aside. I think that's really striking about Ilya is how broad his research is. He's behind some of the deepest theoretical work in similarity search, but also has gone deep into practical implementations. And in recent years, he has published not just in top theoretical computer science venues, but also in leading venues for machine learning and computer security. And today, Ilya will talk about such a results, which appeared recently at ICML 2020. So before we start, I just want to let all of you know that the talk, including questions, are being recorded, and we will make everything available on the SISAP 2020 website when it has been resurrected, that is. So without further ado, I give the word to Ilya.
Thanks, Rasmus, for the introduction. Can you hear me? Yeah, great. Okay, I will talk about nearest neighbor search for optimal transport distances, which is based on our ICML 2020 paper. And this is joint work with Artur Bashkus from TTI Chicago, Yihe Dong from Microsoft, Petr Indik from MIT, and Tal Wagner from Microsoft. And basically, here's the link for the archive preprint of the paper. And also, we have implementation accompanying it, which can be found at this GitHub link. So basically, this whole conference is about, well, most of it is about like similarity search, but the twist of my talk will be that it will be with respect to some set of like class of distances that is maybe not necessarily usually considered for the nearest neighbor problem. So that's why let me spend several slides on actually introducing this class of distances, optimal transport. And the starting point is very simple. Basically, it's the minimum cost matching. Minimum cost matching is a very simple and well-known and well-understood concept. We basically have n red points and then blue points in some metric space. For example, in this case, it's on the plane equipped with Euclidean distance, but in general, it doesn't have to be Euclidean distance. It could be potentially any metric space. But the point is we are trying to find optimal matching. So what does it mean? We are trying to match red and blue points in a one-to-one way, so to minimize sum of all the distances. And basically, everyone who has computer science degree probably knows how to do it efficiently in like polynomial time. Maybe some of you who are particularly spoiled with education know how to do it quickly. But the point is, like a priori, this is actually highly non-trivial, right? So if you don't know how to do it, coming up with a way of doing it is tricky, right? Because a priori we need to enumerate like all possible permutations, and that's very hard if you have lots of points. But of course, like as probably all of you know, you can either write linear program or you can use minimum cost flow algorithm. So basically, this problem can be solved efficiently. And in this talk, I will be considering certain natural generalization of this minimum cost matching, which is called Wasserstein distances. So now the difference is we don't necessarily have the same number of blue and red points. There can be different number of them. So then we don't necessarily have one-to-one matching. And moreover, just to simplify like conceptually picture and at the same time generalize it, let me consider not only sets of points, but also distributions over sets of points. So on this picture, I don't know if you can see it well, but different points have different like brightness, and this corresponds how much mass we put in them. So basically, total mass of all red points is 1, total mass of all blue points is also 1. And now we want to transport red points into blue points, again, minimizing sum of total distances that points travel, but now we weigh these distances according to how much mass we move along the edge. And so more formal definition is the following. So we have some metric space M, and we have two distributions over it. For example, like in this talk, we will be concerned with finitely supported distributions. And then we are looking for a distribution over product space, M times M, such that its marginals are our given distributions. And we are trying to minimize the following functional. So basically, we are integrating with respect to this product measure pth powers of the distances in our metric space. For example, like if we are concerned about sum of distances, then p should be 1. But in general, in some applications, it is convenient to have p different than 1 and p other than 1. And it's not hard to check that this so-called pth Wasserstein distance is actually a metric, but now it's a metric defined on distributions over our underlying metric space. So again, let me emphasize, there is some underlying metric space. For example, in this case, it's Euclidean plane. Then we define Wasserstein distance over it, and this gives us a metric over space of distributions over the plane. And this talk will be mostly concerned with the case p equals 1. This case has some other names. It's called the Earth mover distance or Kantarovich-Rubinstein distance, depending on what community you are looking into. And it has some further additional nice properties compared to general case of general p. We would not like, we will see later how this p equals 1 simplifies our life a lot. Okay, so this is a brief introduction of the class of distances that we will be considering. But now let me give you some glimpse on applications. Why do we even care about working with these distances? What's so important about them? And turns out that in some for some structured data, Wasserstein distance provides a very good, very high quality measure of similarity. For example, traditionally, starting from this paper by Rubner, Tomasi, and Guibas from 2000, people observed that actually Wasserstein distance gives a good quality similarity measure between images. And basically, they just observed that you can interpret image as distribution in the color space. So basically, each pixel corresponds to some point in the color space. Color space is this space of like 256 by 256 by 256, like three-dimensional kind of, where we put point with like RGB coordinates. And then they realized that if you define every image as a distribution in this space, then Wasserstein distance corresponds to like how visually similar images are, like in terms of color and stuff like that. And they actually also spend some time on computational complexity of many related questions to Wasserstein distances. And more recently, in 2015, this paper by Kusner, Sun, Kolkin, and Weinberger, they actually gave another pretty cool application of Wasserstein distance, which I will spend a little bit more time on now because it will later be important for our talk. They realized that it also gives a good similarity measure between text documents. And let me explain a little bit how it works. Suppose you have like maybe 2 sentences or 2 short texts, maybe 2 paragraphs or something like this. For example, in this case, it's like Obama speaks to the media in Illinois and the president greets the press in Chicago. Sorry, these are like from 2015 paper. Now the reality is a little bit different, but okay, it doesn't really matter. So the point is we want to measure similarity between these 2 sentences, but the problem is traditional things like bag of words completely fail to capture similarity between these distances because modulo stop words, they don't share any common words, right? But nevertheless, we kind of feel intuitively that the sentences should be close. So how do we address this? So what Kusner et al. Proposed was to consider what's called a word embedding. Word embedding is a way to assign each word in a natural language high-dimensional vector, for example, 100-dimensional or something like this. And the premise here is that we expect semantically similar words to be close, right? In the, say, Euclidean distance, for example, or cosine similarity or something like this. And so then each sentence can be interpreted as distribution over these word embeddings, right? So pictorially, we can draw something like on the screen. Of course, in reality, the picture is high dimensional. This is just like a simplified cartoon, kind of, to give you some idea what's going on. And then Kusner et al. Actually realized that, so they show in this paper that Wasserstein distance between these 2 distributions actually gives a very meaningful distance between text documents. And specifically, what they claim is that you can use this distance to do k-NNS classification, right? For example, if you want to like you have a bunch of Amazon reviews and you want to understand, like, for new review, which topic is this, you can just find k closest reviews with respect to this Wasserstein distance over word embeddings, and then kind of like look what topics they are, and this will be a good prediction what topic your new text is. So basically, punchline of this paper is that k-NNS classifier with respect to Earth mover distance defined over distributions, like I just told you, is a good classifier for like many learning tasks for text documents. But this is great. But even the original paper, this paper by Kushner et al., already observed that this actually poses a very significant computational bottleneck. So basically, this question of k nearest neighbor like falls out naturally. We didn't really like, you know, let's list all the possible distances people care about and solve like nearest neighbor problem with respect to it. But actually, already this original paper posed explicitly the necessity of like solving this problem. And again, like I'm sure you have seen throughout this conference already a definition of this problem many times, but let me remind you just in case. So we have, in this case, we have n distributions over d-dimensional space. And this is our data set in quotes. And we have a query distribution. And we would like to find k closest data set distributions with respect to Earth mover distance. And again, let me emphasize one last time that there is underlying metric space. And there is additional metric space that is built as Earth mover distance between distributions on the original space, right? So basically, we're solving nearest neighbor problem in this second space. And the underlying space in this case would be like d-dimensional Euclidean space, or maybe L1 space, something like this. And yeah, so we would like to solve k nearest neighbor search problem, abbreviated k-NNS. And this is actually a difficult problem. And like traditionally, this problem has been studied for Euclidean distance, L1 distance, Hamming distance. But here the problem is just like, not even nearest neighbor problem is hard, but just computing distance is already hard in itself because it's a like fairly hard combinatorial problem. So that's why this problem actually has a little bit different specifics from Euclidean case or from the other cases that people traditionally looked at. And I think that's what makes it particularly interesting, because the resulting trade-offs are a little bit different from the usual setup, as we will see later in the talk. So yeah, so basically, like, let's start with basics. How can we do exact nearest neighbor search? Like, let's not worry about efficiency too much. Let's just like even discuss what can we possibly do for starters, right? So basically, of course, what we need to do, we need to compute n Earth mover distance instances, right? And as I said, there are like a few ways you can do it. One way is to like, if you want like to do it in a completely brain dead way, you can always write a linear program in code for each possible edge, how much flow goes into it, and then like write obvious constraints and solve it. But then it would be just like too slow, even if you use fast LP solvers. What turns out you can do though for this problem is that you can use like mean cost flow algorithms for the graph problems, and which are like much more combinatorial in nature, and they give much faster solution. For example, like a very good algorithm that works in this case, it's kind of like simplex method for linear programming, but instantiated for these graph problems, and it's called network simplex, and it was introduced in 1976 by Cunningham. But even though it's much faster than linear programming, it's still slow. So it's much slower than computing Euclidean distances or like Hamming distances, as you probably can easily imagine. Okay, so this is exact k nearest neighbor search. Not much to say here. I just wanted to emphasize that like basically the right way to compute Earth mover distance is to use minimum cost flow algorithms. So then people realized that we actually need to speed up EMD computations. Okay, so again, as we know, for Euclidean nearest neighbor search, there are like two kinds of algorithms. Algorithms that still do linear scan, but much faster than computing all the distances naively, and indexing-based approaches. So maybe in this case, like we can start with asking easier questions. Suppose I still want to do linear scan, but I want to avoid exact distance computations. I want to find some fast approximate proxies that will give me a good idea what my nearest neighbors are. And what can we use for this approximate EMD computation? Turns out that there are quite a few algorithms for this. For example, one very important and very popular algorithm is based on what's called sinkhorn iteration. I'm not going to tell you, like invented by QuadTree in 2013. I'm not going to tell you what it is, but it's like a very simple matrix-based approach, like which is more or less alternating minimization, and it works quite well. And then in Kushner et al. Paper, and then in some follow-ups, people also developed some kinds of greedy algorithms. So it's like very natural idea, you know, like you can just match each point to the closest one. Of course, it wouldn't be a matching, right? Because you can match one point to several and so on. But at least it's a lower bound for the matching. And then they use this lower bound to kind of prune some points that cannot possibly be nearest neighbors. And then this idea was developed further. But yeah, so basically, this gives us some approximate ways to compute Earth-mover distance. And interesting thing here is that these approaches, they don't use the fact that distance matrix is coming from a metric, right? So basically, as I said, there is some underlying metric. It could be plane, could be high-dimensional Euclidean space. And then when we match two sets of points, if we write down distance matrix of distances, it has some like triangle inequality constraints and stuff like that. But these algorithms completely ignore it. So that's why I titled the slide like non-metric case. So this work in like full generality of the optimal transport problem. But in our application, for example, if we care about matching, like doing this k-NNS classification with respect to texts, we do have this additional metric structure. So maybe we can do a little bit more in this case, right? So our problem is a little bit more structured. So here, the goal is to even avoid writing the whole matrix of like all possible distances between red and blue points, so to say. Basically here, the approach is usually to take this metric space of Earth-mover distance and kind of embed it into a simpler space. So for example, Kushner et al. Paper, they have approach along these lines, which is like very simple. So it says that if you want to compute Earth-mover distance between two distributions, let's just collapse each distribution into a mean, and then say that distance between means is a lower bound for optimal transport distance between red and blue points. And this is very fast and it's very simple to compute. It doesn't work super well, but it's a good, very cheap way to estimate Earth-mover distance. But then, like, if we go back and look back a little bit on like more classic work, specifically this paper by Indyk and Tapper, they have a very nice data structure. Yeah, they have a very nice way to compute Earth-mover distance quickly. And it is based on what's called the QuadTree. And I will tell you what it is in a second. But let me tell you that conceptually what it does, it embeds Earth-mover distance into L1 distance. And that's how it does it. So basically, we have this underlying metric space on which we define Earth-mover distance. And then we use this intuition that up to some factor, any metric can be approximated with a tree metric. So tree metric is just shortest path metric on a tree with weights. Like for example, we can have tree like this, and then it defines some metric on the vertices. So basically, it's known that like up to logarithmic factors, finite metric spaces are essentially tree metrics. Again, defined appropriately. I'm not going to spend too much time on it. We'll talk a little bit later about it. But it means that Earth-mover distance over our original metric is close to Earth-mover distance over this tree metric. And Earth-mover distance over the tree metric, actually, it's like easy to see. And again, we will see it later in the talk. For now, I'm just like laying out the philosophy of what's going on. So Earth-mover distance over the tree, it's actually, it turns out to, like, basically, it's very easy to find minimum cost matching on a tree. It's basically like bottom-up greedy algorithm. And it can be realized as computing just L1 distances between certain vectors that we can define for our measures. And that's it. So basically, this gives us that EMD over our metric space is like approximately corresponds to, can be encoded as L1 distance in some auxiliary space. So that's it. That's what this QuadTree paper does. Again, how it does it, that's a separate delicate question and we will see later. But philosophically speaking, this is what's happening. And it gives us very good approximation for EMD, which again bypasses writing down the full distance matrix. So yeah, just basically we need to compute. So basically for our measures, we need to compute, we have certain transformation that computes some auxiliary vector, and then we approximate Earth mover distance between our measures or distributions by L1 distance between these auxiliary vectors. And that's why it's very fast. So we just need to compute L1 distance, and L1 distance is cheap. You don't need to compute mean cost flow. And the point of our paper is that we provide certain improvement for this QuadTree algorithm, which we call FlowTree. Basically, it's not an embedding into L1 space anymore. And that's a little bit unfortunate because the fact that this is an embedding has some additional useful consequences. For example, to solve nearest neighbor problem, now we can just use certain data structures for L1 nearest neighbors. But FlowTree, unfortunately, our improvement does not give that. But nevertheless, it gives us very fast approximate algorithm. And actually, it's like almost as fast as QuadTree, but gives much better quality of approximation, as we will see later in the talk, both theoretically and experimentally. So this is the main goal of my talk and the main result in our paper. But before I'll talk about FlowTree, let me introduce actually QuadTree properly for you, right? So to understand the baseline upon which we are improving. And before that, even let me give you let me talk a little bit about these three approximations, general philosophy. So basically, the idea is we can approximate any metric space with a tree metric. And this was initially realized in a beautiful paper by Bartal from '96. Then later people built up on it and actually obtained optimal bounds. So basically the resulting optimal bound is from two independent works by Factorio, Fall, Rao, and Talwar, and Gupta, Krautgamer, and Lee. They kind of say that essentially endpoint metrics up to a log n factor, they're trees. But let's actually think for a second what it means, right? So conceptually, yes, this is easy, but what's really happening here? And you may say what the hell are you talking about, right? So let's take just a cycle of length n. This gives us some metric space. How can you possibly approximate it by a tree, right? No matter which edge you cut to make it a tree, you incur a very high distortion between some points. But turns out that the right definition here and what works well is to kind of, instead of embedding, allow probabilistic embeddings. So for example, if you consider the same example of cycle of length n, but instead of removing any given edge, you remove random edge, then on average, you incur distortion only 2 for every pair of points. And that's exactly the definition here. And with this definition, we can obtain this logarithmic approximation. And let me just say that this line of work, I think it's very exciting. It's beautiful work. It's one of my favorite sequence of theory papers of all times. But somehow people didn't really perceive it to be very practical because first of all, it's log n approximation. Second, the constructions that I introduced in these papers, they're conceptually simple, but I don't think they're extremely well implementable. Again, maybe I'm wrong here, but that's my intuition. At least somehow my perception was, and I know perception of many other people who cared about it, was that this is great line of work, useful, extremely useful for theory. It has maybe thousands of applications in theoretical computer science, but maybe slightly less useful for practice. But then what people realized, and that happened over the last few years, that actually this idea of tree approximations also is extremely useful for practice. And moreover, not just some tree approximations, but actually tree approximations with useful probable worst case guarantees. And the culprit here is this QuadTree algorithm precisely. And let me just spend one slide on describing this QuadTree. So basically we start with endpoints lying in RD, and in RD we have L1 or L2 distance. Actually, first I'm going to talk about L1 distance, but you know that L2 distance in RD is L1 up to a random rotation. So basically line between these two distances is a bit blurry here. So say we have these 3 points. So how can we represent it as a tree? So we start with just enclosing all the points with a big cube of side length delta. And we, at the same time, we start building the tree. So we build a root node that corresponds to this cube. Then we divide this cube into subcubes of half as short edge length. So of course we can have exponentially many of these cubes, right? But they cannot be all full, right? So basically most of them will be empty just because we have only n points. And so in this case, we have only like two children of this root node. And so one of these children, in one of these children, we are done because we have only, we isolated one point. So we stop partitioning as soon as we like isolate a single point. But the second node, we need to continue partitioning. So we impose a grid of the next level of size delta over 4. And here we have only one non-empty cube. So we basically just have one child. And then finally, we partition it further with side length delta over 8, and we isolate all the points. And this is our resulting tree approximation. So basically, now my point is that distances between points in the original space kind of correspond to tree distances in the new space, in this tree metric. Of course, in order to get provable guarantees, you need to start with not just like, you know, some enclosing cube, but you need to randomly shift it. Because, you know, the problem can be pretty severe otherwise, right? You can have two very close points, but they got separated at a very high level. And then you are really doomed, right? Because, like, you know, original distance is small, but in the tree, you have to jump over these edges with very high weight. So in order to avoid these situations, we kind of like wiggle our original grid by a random vector. And then, like, basically, if your distance was close, it's very unlikely that you will cut in the middle. That's roughly the intuition. And you can actually prove it. It's not so hard. What is the provable guarantee that we can write here? So basically, traditionally, for example, in the original Indic Tapper paper, QuadTree was analyzed in the low dimensions. So basically, it was kind of on the plane or maybe in 3D. But actually, this paper by Andoni, Indic, and Krautgamer realized that you can actually get some useful guarantees even in very high dimensions with only mild dependence on the dimension. So specifically, what they show is that expected distance in the tree is at most log times L1 distance of the original vectors. And only with very small probability, tree distance is much smaller than the original distance, okay? So basically, like up to logs, our tree distance is L1 distance between the vectors. And as I said, L2 distance is like, basically, if you care about L2 distance, just do a random rotation and then compute L1 distances, and this will be a good approximation. So this is QuadTree, like very simple, very practical, like very nice algorithm with like pretty nice analysis with these log factors. But what does it give us? Like, okay, I started with Earth mover distance, and now I fell into this detour to talk about tree approximations. How is QuadTree useful for optimal transport or Earth mover distance? Like, why is it good for us? And basically, the idea is very simple. If you start with a bunch of random blue points and you want to compute optimal matching between them in Euclidean space, you can just compute this tree approximation and solve your matching problem on the tree. But on the tree, it's very easy to solve. So basically, we just need to match points greedily bottom up. It's kind of obvious if you think about it. It's particularly obvious for our specific case because we do not have general tree. We have this so-called hierarchically separated tree where like weights along the edges, they decay exponentially as you go from the root to the leaf. And it's obvious that we need to match as much as possible in the bottom levels and then match all the leftovers on the next level and so on and so forth. So for example, for this picture, we need to match these 2 points and then we need to match these 2 points, right? So proving that this greedy gives us exactly optimal matching on the tree, it's just like an exercise. You can think about it like for 10 minutes and I'm sure you will all get it. But why is it good for us? It's good for us because we can implement this greedy algorithm as L1 distance between 2 auxiliary vectors. So for example, for the red points, we can define this vector. So we basically create coordinate for each node in the tree. And then we effectively, in each coordinate, we put total mass of the red points in the subtree multiplied by weight of the level. So for example, for the root, we have total mass is like 1. And then we multiply it by like 2 delta, which corresponds, like, okay, again, like maybe I got the constants wrong, but you get the idea. So basically you need to take total mass in the subtree and multiply it by scale of the level. And we can do the same for blue points. And then the point is difference between these 2 vectors. So basically, if you compute difference between these 2 vectors and compute L1 distance, this will be exactly cost of the matching obtained by the greedy algorithm. Basically, because points above where the matching happens, they will cancel out. And then, like, basically, again, this is like a simple exercise. I'm not explaining it super well, but you can check it. It's kind of pretty easy. So, like, I showed you some guarantees for the QuadTree, but what does it give us for Earth mover distance? Basically, for Earth mover distance, we can obtain pretty simple corollaries from these estimates by Andoni, Indyk, and Krautgammer. We can get that in expectation, our EMD estimate is at most log times the true value. And with high probability, we do not underestimate too much either. So basically, here we obtain that we do not underestimate by more than log S factor, where S is support size. And the reason why this support size comes into play here, because we, for the QuadTree, we have this underestimate probability, and then we need to take union bound over all possible pairs that, you know, like, we do not underestimate L1 distance or L2 distance, underlying metric distance for every pair. And this gives us basically this log S bound. So basically, again, like, we get like polylog approximation for Earth mover distance, and this actually works very well in practice as well, as we will see later. Okay. So yes, just to conclude the QuadTree discussion, let me say that it gives this log d times delta times log S approximation for a single EMD computation. But when we are solving nearest neighbor problem, we need to remember that we need to compute n distances. And so we lose this additional log n factor, again, because we need, instead of now taking union bound over like S squared things, we need to take union bound over like S times S squared times n things. And basically, our approximation becomes worse and worse as we have more and more dataset points or dataset measures. And we actually observe this deterioration in practice. So that's the state of the art for QuadTree. And now let me tell you how we're improving it and like what it implies theoretically and in practice. Okay, so now I'm introducing FlowTree, which is basically our contribution of our paper. And the idea is simple. Like, I'm almost shocked that no one thought of it before. Like, it's almost obvious in hindsight, but with like many good things, you know, like it took us some time to discover it. So basically, before we were looking for this optimal matching, right? And then we were computing cost of this matching with respect to the tree metric. And now the modification is very simple. We find the optimal matching as before. So we kind of say that I want to match this red point with blue point and this red point with this blue point. But now instead of computing matching cost in the tree, we compute its true cost in the original metric. So for example, in this case, we remember that we started with some points in the Euclidean space, then we approximated them with the tree. And like now we find matching in the tree, but we compute its cost in the original metric. And the QuadTree does not do that. It computes the cost in the tree metric, which itself is an approximation of the original metric. So formally, we just find the optimal matching in the tree, and then we just literally like say that, okay, between this red point and this blue point, what was the original distance? Not distance in the tree, which would be delta over 2 plus delta over 2 plus delta over 4, right? But what was the original Euclidean distance that these points originated from? So that's the whole modification. So it's like really small modification, but it turns out that it has like several nice consequences. But let me start with like negatives. So negative is that it's not an L1 embedding anymore. So basically we cannot easily write down red vector and the blue vector such that like L1 or like any other distance between them corresponds to this FlowTree distance, right? Like, again, if you just think about it, it will be pretty obvious. So that's a downside because it doesn't reduce our nearest neighbor problem to L1 nearest neighbors. But nevertheless, it turns out that this is a very useful approximation technique for Earth mover distance, and it really speeds things up. Someone is typing something in the chat. Oh yeah, is the QuadTree embedding optimal for embedding EMD into L1? It's not known. It's like, even for the plane, basically we have some upper bound by QuadTree and lower bound is like square root of the upper bound. Actually, in high dimensions, I think it's also known up to a log. So there are some gaps, so it's not known. Okay, another question, is it clear that p equals 1 is EMD? I assume for EMD, every entry in mu is either... Well, I mean, okay, so let's discuss this offline, but it's a question of terminology mostly, to be honest, yeah. Okay, great. So, okay, so we introduced the FlowTree. Let's now understand how well it works and what it gives us even. So let me start with theoretical guarantees. What can we prove about it? So like, can we prove that it is better theoretically than QuadTree, for example? So for QuadTree, we got these two nice bounds for individual distance computation and for approximate nearest neighbor search. For FlowTree, we can improve these results a little bit. So first of all, we can get rid of this log n in the approximation for nearest neighbor search. So now our approximation does not depend on the size of the data set. And we can prove this theoretically and empirically. We can also see that. And it's actually theoretically, it's pretty easy to see why this happens, because we never underestimate. Because we always find some valid flow and just compute its cost. It is not like we're always at least opt, and at most opt times something, right? So basically, we don't need to take union bound over like all data set points, and that's why we do not lose this log n. And moreover, we can improve this bound further to basically, like, we can show some dimension independent bound. We can show that approximation for FlowTree just depends on only on like support size. So basically, in any dimension, if you give me like a measure on like 5 points red and 5 points blue, then the approximation would be like log 5 like squared, right? And it also builds on a very nice idea that was discovered by Bachkurs and Indik in 2014. They used a certain trick in low dimensions, but then we showed that in high dimensions this also works, and it gives us dimension-free estimate. See the paper for the details. I'm not going to talk much about it. And let me also say, what do we know about worst case analysis? Okay, I'm not going to talk much. Let me just mention that, you know, like these logarithmic bounds are nice, but in practice, we don't want logarithmic approximations, right? So in practice, we want like, you know, exact nearest neighbors. And we have certain model that capture reality a little bit better than worst case, or so we think at least. Again, see our paper for details. So we have some kind of like distributions over instances, and we show that in that, like for this distribution, which we kind of like claim is like, kind of corresponds to real world text documents, but of course it's still like, you know, just some random model. So it's not, it's some like rough depiction of reality still. But for this rough model, we kind of show that FlowTree recovers true nearest neighbor with much higher probability than QuadTree. And moreover, again, both empirically and both in practice for this specific random model, we see that quality of FlowTree doesn't deteriorate as we increase number of dataset measures, but QuadTree deteriorates pretty quickly, actually. So this benefit of like not losing log n is actually real, kind of. So this is it for the theoretical guarantees, and let's talk a little bit about implementation. So I have 20 more minutes. This is great. So yeah, so we basically implemented this algorithm, FlowTree, QuadTree, and a bunch of other baselines. In C++, we spend a lot of time make implementation as fast as we can, and we also provide certain Python wrapper that like we and anyone can call these algorithms easily. It's on GitHub, so you are more than welcome to try to run it and experiment with it, try to improve upon it, or, you know, just like run it on your favorite benchmark and report some good or maybe bad results. Yeah, so for baselines that require some matrix operations, like for example, sinkhorn iterations, we actually use NumPy with underlying very fast BLAS implementation in order to be like as fair as possible to these algorithms. And yeah, so basically there is a whole orthogonal discussion, like what kind of hardware you should use for tasks like this. But we kind of decided to keep it simple and just like focus on single core CPU implementation. Some of these algorithms are more GPU friendly, some are like maybe more CPU friendly, but let's keep it simple just to, you know, like to have some clear message, you know, at least for some cases. So what's the task that we are solving, and what's the task we are going to evaluate our algorithms on? So this is just k-nearest neighbor from before, right? So, but we specifically do it for documents and images. So we have n text documents or images, and we have a query, and we want to retrieve k most similar ones with respect to Earth mover distance. And for text documents, as I said, motivated by this Kushner et al. Paper, we interpret any text document as uniform distribution or word embeddings of the underlying words. And for word embeddings, we specifically use glove word embeddings. This is kind of like one of the staples of NLP at this point, introduced in this paper. Yeah, for simplicity, again, I don't think this matters a lot, but just like, let's focus on k equals 1. So suppose we just want to retrieve one closest point. I think we did some experiments with k equals 10. It was almost the same. So just, again, for simplification. And we have two kinds of experiments. The first experiments are just like, let's evaluate algorithms against each other, right? But what does it mean, right? So some algorithms are faster, some algorithms are slower, some are more accurate, some are less accurate. But at the end of the day, what we are looking for here is trade-off between accuracy and efficiency. So it's natural to assume that the more time you spend, the higher accuracy you will get, right? And so let's understand what's the trade-off here. Like, how fast can we be if we want that much accuracy? And then, as in Euclidean nearest neighbor, as many of you might know, we don't usually just use a single algorithm. We put algorithms in the pipeline. So maybe we start with like very fast algorithm that gives us some list of candidate points, and then we narrow down this list of candidates using like maybe more and more precise but slower algorithms. And then finally, we do the exact distance computation on the remaining points to obtain like maybe one nearest neighbor. And so this is what I mean by pipeline here. So basically, what's the optimal way to compose our algorithms, maybe new ones together with old ones, in order to obtain best end-to-end overall retrieval time, right? So basically, I will show you two series of experiments. First for individual algorithms, just, you know, for science, kind of, understand what is faster, what is more accurate. And then, like, if you want to actually do such a retrieval thing in practice, how do you need to put these things together? Yeah, and pipeline is exactly what I've just told you. So we feed our data set into some first algorithm. For example, it could be based on indexing, maybe. And it retrieves us K1 candidates, and then we narrow it down to K2 candidates, and maybe then we use exact algorithm and just obtain nearest neighbor, right? And we hope that in most cases, our previous algorithms were not stupid enough to actually rule out this nearest neighbor from the list. So what are the data sets that we are using? So we use two standard data sets. They're standard in this optimal transport literature. These are text documents like 20 News and Amazon. And see that here, these data sets are size 10,000. And 10,000 points, it's nothing for Euclidean nearest neighbors, right? You can just like process them in like, not even like 1 millisecond, much less than that, right? So basically, this is a scale that is ridiculous for Euclidean nearest neighbor search. But for optimal transport nearest neighbor search, it's much more computationally intensive task. And actually already these data sets are fairly challenging. So that's why they were perfectly adequate for our study. And these are Amazon reviews and like some news articles retrieved from somewhere. I don't know from where. And then for images, we use MNIST. It's also like a standard benchmark. It's not exactly the same way to use Earth mover distance upon images that I told you in the beginning of the talk, but here we just interpret every digit as a distribution over the plane, and then like basically we just compute Earth mover distance between these distributions. Turns out that this is also like it's again a standard benchmark in this literature, and it's a somewhat of a decent similarity measure on NIST digits just because they're like so well written. So what are the algorithms that we evaluated? So oops, sorry. So there are like, I would say, three classes of algorithms here. So first class of algorithms, it's like fast linear time algorithms. So I'm distinguishing between fast linear time and slow linear time. So let me explain what I mean by this. So fast linear time algorithms that are particularly fast, and they're like linear time naturally. So for example, I told you about like, you know, we can collapse distributions into means and compute distance between them. This is extremely fast, as you understand. Like QuadTree, you can also make very fast because you can pre-compute these feature vectors and then just compute L1 distances between these vectors, which is also super fast. And then we also have a bunch of other baselines. It doesn't really matter what they are. They're not going to be that prominent in the final result. But basically, all these computations are pretty much just like computing. To compute a single EMD estimate, you compute single L1 or L2 distance. So it's very fast. Now there is this slow linear time algorithms. This is where our FlowTree falls. It's like a little bit peculiar, right? To call it like slow linear time. What do I mean by this? So formally, it's still linear time, right? So we have a tree. We can just find optimal matching and compute Euclidean distances between these points. But in practice, it's quite a bit slower than fast linear time algorithms because, you know, it's not just L2 computation anymore. You need to do some work. You need to, you know, like run some depth first search on the tree, you know. So it's like, in practice, it's like noticeably slower. So we'll see exactly how much slower it is. And this raises a natural question. Is it even worth it to like spend more time, right, than this fast linear time algorithms? And we will see later that it is worth it. And then there are these non-metric algorithms that don't use the underlying metric structure. And they're like much slower because they require, for starters, to write down all possible distances between red and blue points. So these are greedy algorithms and sinkhorn iterations. Yeah, okay, so what do we get? So let's first talk about individual algorithms. First of all, what are the running times? So like let's just ignore the question of quality. Let's talk about running times. And running times are exactly what you expect them to be, right? So basically, I grouped the algorithms in this table. First, I put like fast linear time algorithms. Then I put FlowTree, which is like slow linear time, and then like slow algorithms, right? And as you naturally see, like, you know, these fast linear time algorithms, they're damn fast. They're like just a few milliseconds, right? FlowTree, on the other hand, already takes like some fractions of seconds. And slow algorithms, you know, they take like at least like a second, like a good solid second. And exact computation takes like dozens of seconds. So this is like really slow. Why is QuadTree so much faster? Because, okay, so great question. So let me actually maybe spend 1 minute on it. Yes, it is doing the same thing, but we don't need to do it explicitly. That's the beauty of it. So you just do this tree approximation once, and you do pre-computation of these additional feature vectors for all your data sets. And then when your query comes, you just do this pre-computation for the query and compute sparse L1 distances with all the pre-computed vectors. So you never, like during query execution, you never explicitly explore the tree, you only do it for the query. But for dataset points, you don't do it. Okay, does it answer your question? Yeah, and for FlowTree, we cannot do it. We need to explore tree for every dataset point. So that's what makes it slower. Okay, so basically the question is, okay, so like we are in no man's land, right? We are not as fast as these algorithms, and maybe we are not as accurate as like exact computation. So like why on earth do we even care about this FlowTree thing so much, right? But to answer this question, let's look at the next slide. Oops, sorry. So yeah, so this is trade-off between quality and running time. So let me explain what these plots are. So let's look first at the plot on the left. So this is retrieval quality. So what does it mean? It means that suppose I run my algorithm X, for example, QuadTree, and then it ranks points according to these QuadTree distances. And then I retrieve top k candidates according to this distance. On which fraction of queries this includes my nearest neighbor? I think it's called recall at 1 or something like this. I always keep forgetting about it. Doesn't matter. But basically, the more candidates I retrieve, the higher probability is that I actually hit my true nearest neighbor with respect to true Earth-mover distance. And of course, ideally, I would like to retrieve very few candidates. So it's better when my curve is to the left and to the top, right, on this plot. And so we see these trade-off curves for a bunch of these algorithms. So mean is the worst. It's like pretty bad, actually. Then we have like some other benchmarks. Then we have QuadTree, and then we have other algorithms. But see that other algorithms, they're so close to each other that I put them on the separate plot on the right. So this plot on the right, it's zoomed in version of the plot on the left. And the punchline here is that FlowTree actually ends up being comparable in quality with like slow algorithms. But at the same time, it's much faster than them. It's like several times faster, at least, of these algorithms. And it's comparable with the quality of them. So basically, we have like basically this fast linear time algorithms. They give like kind of meh quality, and then like FlowTree and this high quality algorithms, they actually give comparable quality, but FlowTree is much faster. And we will see later that in pipelines, this will be extremely useful for us. And so the same conclusion holds for Amazon dataset, kind of similar situation. So we have FlowTree here, that is again like comparable to slower algorithms and much better than these fast algorithms. Yeah, from MNIST it's also the same, like with some specifics that like do not affect FlowTree. For example, on MNIST, QuadTree actually works very well, which is not really the case for previous two datasets. But again, FlowTree is in any case much better. So that's the individual algorithms, but what does it mean, right? Again, we kind of like saw this like, again, a little bit no man's land, right? So sure, we're like maybe not as accurate as like, you know, Sinkhorn with many iterations, but we are faster, so what, right? Like what, like how does it help us? Why this is a good result? Turns out that this especially, like FlowTree especially shines in the pipelines. So let me remind you what the pipeline is. So it's like, again, we feed data set in the first algorithm that very quickly narrows down to some list of candidates. Then we run more slow algorithm that is more nuanced. And then maybe we do like, I wrote this pipeline just with 3 algorithms. It could be more than that, right? But like, you get the idea. And there are like a few questions here. Which algorithm should we use? And how do we tune the number of candidates that we use in the intermediate stages? So here we kind of have 2 experiments. We either return 1 document and kind of estimate the probability that it's nearest neighbor, or we return 5 documents and we require that nearest neighbor is among them. So it's, yeah. And we require that probability of hitting the true nearest neighbor is at least 90% across the queries. And we do it just for 1 data set. Again, we tried the other data sets, kind of the same conclusion. So let me show you just result for 1 data set. So the point is, pipelines without FlowTree, they end up being much slower. So basically, best pipeline without FlowTree that we were able to find is like several times slower than best pipeline with FlowTree that we were able to find. So especially this happens to be the case when you retrieve 5 points and hoping that nearest neighbor is among them. So there we get like improvement by a factor of 8 or something like this, or like maybe 7 or 8, like basically between 27 milliseconds and 200 milliseconds. When we insist on returning 1 point, it's also like the gap is significant, a little bit less smaller, but it's noticeable. It's not a fluke. It's like actually real. So basically, if you add FlowTree to your pipelines, this actually improves things a lot. And let me be slightly more nuanced here. So basically, these are the pipelines that we tried. So we first start with a fast algorithm, and for fast algorithm, we use mean, QuadTree, or like, again, overlap. It's some other fast algorithm, doesn't matter too much. Then we possibly use FlowTree. Then we possibly use like slower algorithm, and then we possibly use exact algorithm. And we compose pipelines like using all possible combinations of those. And it turns out that QuadTree is the best algorithm for the first stage. So basically for fast filtering, QuadTree ends up being the best, much better than mean and overlap in terms of overall end-to-end time. And FlowTree always improves things. So if you have pipeline without FlowTree, just add FlowTree and it will always be better. It's like good spice. Adding to the food never hurts, you know? And exact algorithm is not always necessary. For example, if we are okay returning 5 points, hoping that nearest neighbor will be among them, sometimes we can just bypass the exact computation and stop early in the pipeline. So these are the results that we get. So let me explain what these pictures are. So basically, left picture is for returning 1 point, right picture is for returning 5 points. And basically, these are the charts where we show how much time we spend on each stage of the pipeline. So basically, the first stage is always yellow. This is QuadTree. And we basically, other algorithms for the first, they're worse. And then, for example, we can use, for example, the first bar corresponds to like QuadTree. Then this like RWMD, whatever, it's some version of the greedy algorithm, and then exact computation, right? And basically, as you see, adding this FlowTree corresponds to this orange piece. So FlowTree, just by spending a little bit of time, allows us to really decrease the subsequent time spent on subsequent stages. For example, in some cases, QuadTree even makes, FlowTree makes even further stages not necessary. For example, when we retrieve 5 points, turns out that the best thing to do is just run QuadTree with some number of candidates and then filter these candidates using FlowTree, and that's it. And as you can see, generally the trend here is that adding FlowTree really shrinks our bar, and it kind of preserves the quality. And as a result, we get much better running time and the same quality. So again, that's sorry if like I kind of skimmed over it like a little bit too fast, but again, like look at the paper. But again, I hope that the overall message is clear. Just adding FlowTree to the pipeline really helps here. So what's the key takeaway? So I would say that like when we worked on this project, I realized that like what makes this problem interesting, I already mentioned it in the beginning of the talk, but we kind of have slightly different trade-offs between efficiency and accuracy compared to classic Euclidean k-NNS problems. For example, the reason is exact distances are so hard to compute. So for example, these pipelines I showed you on the previous slide, in the same time that these pipelines work, you would be able to compute only maybe 3 exact distances, you know, unlike say like maybe 1,000 Euclidean distances. So basically, that's why these approximation algorithms really shine in this domain, where we have like cheap but maybe crude approximations. They're still extremely useful for the overall end-to-end running time, even though we might want like high accuracy in the end. And I think that's what makes this problem a little bit different from Euclidean k-nearest neighbor search, and that's why I really like studying it. And in some sense, diversity of the pool of algorithms that end up being useful, it's like very, very significant in this case, which I think is very nice. So what's the conclusion of my talk? So we basically showed certain modification of this classic QuadTree algorithm, which we call FlowTree algorithm, which is like very simple. And it's very good at estimating Earth mover distance in high dimensions. And it yields both theoretical and empirical improvements. And we also packaged it reasonably nicely, at least by like research code standards, as a like C++ implementation with Python wrapper. And we not only do it for FlowTree and QuadTree, we also like expose API for all the other baselines that we invite you to try on whatever dataset you care about. And it's published on this GitHub link. And we actually made some special effort that it, you know, builds seamlessly and compiles and runs in like a bunch of different operating systems. So hopefully you will not have much trouble with it. And with this, let me conclude my talk. If you have any subsequent, like further questions, maybe now you can ask me over chat, I guess. Yeah, that's it.
Yeah.